Hello, my name is Brugard. I'm the CEO of Wolfram Core, developers of SystemModeler. Today I'm going to talk about SystemModeler and what's new in version 12.
Okay, SystemModeler has been developed to model all sorts of applications. It could be replacing a rat with math. It could be modeling of a gas turbine. Sometimes it's very expected things people are doing. Sometimes it's more unexpected. For instance, doing music with SystemModeler. And one of the new features that is coming with next SystemModeler version has actually been used for that purpose. So today, I'm going to present the new version. I will focus on three things: model creation, model exchange, and model optimization. So the first is, how do we get a nice workflow when we create a new model? Once you have a new model, you want to analyze it, but you might also want to distribute it to someone else. So then it's important to get exchange of models in a good way. And of course, when you have a model, you might want to have maximum performance or optimize it in some other way. And that's also an important task that we added features for in 12. My name is Brugard. I'm the CEO of Wolfram Core. And before I start with those three, you might have noticed this SystemModeler 12, jumping from, I think we are on 5.2, it might be 5.1, I always confused. 5.1, yeah, and we jumped to 12, so why do we do this? So let me take a step back to Mathematica 11.3 first then. So in 11.3, the system modeling functionality of SystemModeler was integrated to the Wolfram language itself. This means that even if you don't have a SystemModeler license, you can run a lot of the SystemModeler functionality in a Mathematica notebook. But so as sort of an introductory example, it could be, for instance, getting a model, systems inverted pendulum. I query for this model, which is built into the system, and it will give me that answer. Or I should have had it like that. I can use that to get a plot, for instance. And now it takes this model, it compiles it, and it will give me the plot for some interesting signal from it, I hope. So all these sort of functionality was built into Mathematica. That's a bug, to Mathematica 11.3. That came with a few benefits. It now seamlessly integrates with Mathematica workflows, so other functions. It's easy to access all other functions in the Wolfram language and combine them with SystemModeler models. But you can also deploy your models to people that only have a Wolfram language license. So you do your model and you do a notebook with some exercise, for instance, which we'll see soon in Ankit's presentation on virtual labs. So all these things were improved, but it came with a small thing that you needed to have in order for this to work, and when you wanted the SystemModeler user interface to work together with Mathematica, you had to combine 5.1 with Mathematica 11.3. And if we would have kept with that numbering, we would have gone to 5.2 and Mathematica 12. And it becomes hard for people to kind of know which combinations work. So that's the main reason for actual switching. But there's also an important symbolic reason showing that we're actually integrating more and more, and that is what you should expect to see over the years. Okay, so first, I'll talk a bit about the user interface. I do that by opening the SystemModeler interface here and start with this example. So it's basically two masses. One here, mass 1, which is set with a starting temperature of 100, and mass 2 with a starting temperature of 15 degrees Celsius. Then the things in between here is different forms of propagation of heat. So you have conduction radiation, and convection. So imagine you want to understand how these different things influence. Then you can take this model and you simulate it and get some result. So you will see that eventually these two masses will have the same temperature, and you can see how much time it will take with these on. But now you might want to know what happens if I don't have, let's say, radiation. Then we introduce a feature where you can disable specific components in your model. So I can click on this, and I'll say disable component, and it will go gray, and it means that this is no longer part of your model. So then if let me do this first. I'll pin this, so we'll save this, keep that experiment, and I run this again. Oh, sorry. Sorry, my mistake. Should go from here. I run this again, and I want to compare this with the old one. I drag the old version here, and we see the difference. So apparently, in this case, body radiation wasn't an important factor to transfer heat between the two. It was almost the same. But in this way, I can add, remove different things easily. And I can even create parameters that would control things. So if I added one here that is enable heat transfer. So if I set that to false, all my heat transfer is gone. And if I would simulate again, then of course, both temperatures will keep at the original level. So this is one of the new features, easily enabling and disabling components. Another such feature, let's go to a few of the graphical views things. I won't have time to show all of them, so I will just select some. So we have a few customers that make models that are quite complex, with a lot of components, a lot of wires, and they're crossing from all over the place. So if you would have this in SystemModeler 5.1 and try to move one component to rearrange, then the time it took for it to calculate where all the crossings and modify the things was not really doable. Now you can take, let's say we take a few of these and say, I want to move these somewhere, then I can do that with ease. So this makes it easier if you are developing complex models. I'll take this too. If you remove a component completely, so before, if you remove this resistor, what would happen is that all the connections to the resistor would be gone, and I will get this, and I would have to create this connection to get the complete circuit. Now we added intelligence, so we actually understand that if we remove this, we should actually create and keep this connection. So there are all sorts of small things that everything itself perhaps is just one tiny thing, but a lot of these things included in the user interface to make it easier to develop and maintain your model. We'll keep that for later. Sorry. This one. And another thing, a few releases ago, we added the ability to predefine and store plots into the models. But animations, you could not do that. So this is a model we did to see if people could actually bend the ball like Beckham. So it's basically a football and a real football, not the sort of odd football you have here. And we tried to hit the football to score a goal from a corner. And now this was open, or it simulates it, and if I look at it in the animation here, it's sort of odd. I have to start to kind of zoom in. I see the pitch, and I might play this, and it's hard to see what happens. It suddenly says goal, but we didn't. So I have to find the right angles and so on to get this to work. Now with the ability to actually set camera positions and store them into the model, it looks this way instead. And the way you do that to store them is really easy, so I will show that too. So here, it automatically starts to play with the camera angle that we chose and following the object that we chose. And we also chose to put it on repeat. Goal! Yes, you're not Mexican, right? And you can, of course, then start to rearrange that to really see the goal. But you can also save several different cameras. So I can say, now I have the ball camera, I can take the overview camera, and I've saved that too. And now I can see it from another angle. So I can set up as different view spots, and I'll get that automatically. I don't have to redo that every time I show the model. Good. So yeah, there are a bunch of those things in the graphical user interface. If afterwards you download the presentation notebook, I have a larger list. It's not complete, but it's a larger list of which things are actually added to the user interface. And for that matter, for the other things I'm presenting to. So as I said, exchanging models, once you created a model, exchanging models. Before we had the possibility to export models in something called FMUs for co-simulation, meaning that we export a model with the actual solver in it, so other softwares that might not even have a solver can actually use that, run that, and sync with whatever they are doing. But we couldn't import in the same way. So now we added that. So we can take a look at basically how that works, the whole flow. Oh, I actually, let's do this. Hopefully, nope. That's obviously played around here a bit before. So let me just take a new copy of it. Tiling system. And I should learn to spell. Tiling system from, yeah, let's take that one. Copy that. Why doesn't it want to copy? Try again. Yeah, let's put it there. Okay. That was not the one I was aiming for. This was probably, yeah, sorry. Okay, so here we have it. I could then take one of these tanks. This is basically tanks that you've tried to control the level of water in. And suppose I wanted to export one of these tanks. I can open it, and I'll say File, Export as functional mockup unit, which is a standard used by many tools. And I'll export it. And I can save it somewhere, for instance, in my downloads, which is typically my folder of junk. So I'll replace that. Now, once so as I said, we're exporting it with the actual solver in it, so we have to compile and everything like that before we export it. And now, if I instead import it again, so File, Import, FMU, tank, like this, and it gives me a name, tank FMU. Yes, let's replace that. So there we have the new one. It looks similar, but it has the symbol showing that it's a tank, FMU. So now what I can do is I'll replace this, and I can do that with a small trick. Rather than removing it and replacing it that way, I can say change component type, and take this tank FMU, put it here, and add it like that. So now we have the new tank, which is the co-simulation version, and I can simulate this. The important thing of that, of course, is not that I can re-import something that I did in SystemModeler already. It's that I can import something done in some other tool. And it doesn't have to be a Modelica tool. It can be all sorts of tools. There's 50, 60 different softwares that can do different forms of FMU, FMI exchange.
It's x86 specific, or
It works on different platforms, but you have to export it from the right platform. Yep. Looking here at time, I'll do this very quickly. We have improved symbolic linearization quite a lot. So symbolic linearization means that I can take the models typically created in SystemModeler are very nonlinear. And in this case, we have an inverted pendulum, one of our standard examples. And if I take that inverted pendulum, let's add that, and I linearize it in Mathematica, then I will get the, after a while, localizing model, it says. So basically, it's creating the smallest version of the model around the point that we chose to linearize around, and then we're creating the transfer function model or the systems or the state space model, whatever we have set as our preference. Took a bit of time, like that. The neat thing, though, is that we can set things as parameters instead. So we can choose to keep things symbolic. So if I say here, method, symbolic derivative, symbolic parameters, inverted pendulum D, then instead of getting only numeric values, I can keep parts of it symbolic. This means that, for instance, if I would like to design a controller with different options that was depending on the dimension of my pendulum, then I can keep this parameter and play around with that in Mathematica. No, not directly. No. Okay. Then optimizing models was the third thing I was going to talk about. And this is, if the modeling stuff that I started with is really for everyone, and this is more for someone that is really trying to optimize the system, so it's a bit more advanced. It can be used for many different reasons. For instance, understanding the behavior of the simulation better. It can be used to improve performance or to do a better linearization or understand it better. That's just one couple of the cases. And this is where audio comes in. I will give an example. One of my colleagues, Leonardo Laguna Ruiz, he creates sounds or he creates filters for making music. And what he does, he basically takes the old classic real analog filters, re-implements them in SystemModeler with drag and drop. And then he tries to reduce those equations to the most efficient set possible in order to be able to simulate this in real time and with as many filters as possible. So if we look at that, one of the things he did when doing this, he had an amplifier with distortion that he wanted to model. And he did the top one there. But the right one was this one, and we will see what differs. Right now, well, there's colors kind of indicating where the errors will appear. He didn't know that from the beginning. His approach when doing this, the things that are marked there with red and green are transistors. These transistor models look like this. So he used a transistor model, a well-known transistor model called the Ebers-Moll model. And it's developed to be a minimalistic, ideal version of a transistor. So it contains these two diodes and some gains and so on. So using this model, he tried to simulate the system. So simulates here, and we will see. I said he wants to have this real time. Does this look real time? Speed, it's decreasing, 343 microseconds per second. So that's far from real time. It's like not even close, so let's stop that. Doesn't really work as we want, right? Oh. to remap my keyboard. That happens sometime. Let's try again. There you go. Okay, so then let's look at the model in SystemModeler. This is the model with the red dots. I'll simulate it again in SystemModeler, and we will see the same behavior, that it's slow. And this will take us now to the block equation browser. So let me stop this. You see it's 5 to the power minus 3. It's super slow too. So the new tool here is the equation block browser. And this is a small model, so it doesn't have that many things. But what it shows is the equations that are, or the system of equations that you get from your model. In this case, it shows you basically have one big block. It's in blue, which means that it's a nonlinear equation. So if we click on that, it will show us how the different variables depend on each other in this block of equations. And we see there are 4 blue dots here. These 4 blue dots represent the nonlinear parts of our equations. The green dots are different kind of linear systems. And if we click on the blue dot here, and this is very small, so you can't see it when I hover over, some of you might see it. It says which variable we're talking about. But it also selects the corresponding equation. So this for Leonardo, when he saw this, and it happens to be that all these 4 blue dots have similar equations. It's just for in each of these transistors, it's where the diode is, where he gets this problem. And Leonardo is not a mathematician. He's more, he knows his electronics, so he knows the physics behind it. So he thought, okay, what's the typical difference in the different models when you do transistor models? Well, you can actually add transistors or capacitors to your model. So that's exactly what he did. He added these 2 small capacitors, which corresponds to the capacitance of the wires. And as he sort of knew, he was directed by the equations. This is somewhere here is where you should look, and he has the knowledge about his area. He could know that. If he would have been in thermodynamics, he might have been thinking, I need a heat capacitance, for instance. Or if he would have been in hydraulics, some volume. Things like that. And now, by adding that, he could get from this sort of set of equations, it could be reduced to this one. So despite adding these components, the system to solve was much easier to solve. And if we simulate it, like this, building in progress, we hope that it can reach real time. Oh, there you go. Interpreting unit, it's actually done. I don't know what happened here. It's done simulating. And there you go. There's some bug here in my 12 version, apparently. But it immediately kind of, the result was simulating 1 second. The actual simulation is much shorter than 1 second now, with that small of a change. So then the question is, what did he actually achieve with that? Let's listen to it. I hope we get some sound here. Is sound on for it? Doesn't seem like it works. Let's plug it like that. The player has here. Yeah, let's see. The master volume is on. But this doesn't give anything. It's odd. Let's try again. Could sound go? No, it was supposed to do, but I disconnected it. So anyways, we'll have to fix that for the next presentation because Ankit will be trying to do that, and I'm running out of time. So this is actually playing music. You don't hear it, but sorry for that. You can go to YouTube afterwards, and when you download, there's a link to it. So basically, we worked on model creation, many things to make it easy to create models, model exchange, and then model optimization to be able to do things like music. Thank you very much.